All right, how's it going, everybody? We are here at the for our first video associated with week 2 here at the end of week 1. Today we're going to look at section 6.1, beginning chapter 6 here. So just kind of want to say a couple things before we get started on this guy. In general, what we're going to see is that chapter 5 introduced integration. Chapter 6 is going to be giving us some integration applications, like why do we care to know about integration. Then when we get over to, I'm just kind of looking at some of my section titles right here. Then when we get over to chapter 7, we are going to see more trig technique, or sorry, some more integration techniques. For kind of, we're going to kind of run into some problems in chapter 6. We're going to see some quantities that we want to be able to integrate, but that we don't know how. So then in chapter 7, we're going to go back and get more integration techniques. Once we have more integration techniques, we're going to be able to do more stuff. And so then in chapter 8, we're going to go back to applications again. So kind of our path through the first 2/3 of this class for chapters 5, 6, 7, and 8 is chapter 5, techniques. It's like basic techniques in chapter 5, basic applications in chapter 6, advanced techniques in chapter 7, advanced applications in chapter 8. And then the remaining third of the class will be a whole different animal of looking at sequences and series there. But in any event, so this is kind of our introduction to chapter 6 right here. We're going to look at some applications of why do we care to know about integration. Our topic for today is area between curves, and so this one's going to be not too crazy. I think you're going to be able to see a really nice visual representation for this one, but there's a really important thing that's going to happen here today that I'm going to kind of really heavily emphasize the concept of our Riemann objects, like you guys have seen with your Riemann sums. When we represent an integral, thinking of it as the limit of a sum of rectangles underneath a curve, we really want to think in terms of those rectangles. We're going to do that pretty heavily today. And the reason why this is really important is because conceptually we're going to be extending that idea. Rather than thinking of only having Riemann rectangles, we're going to have a lot of Riemann sticks I'll talk about today. We're going to see lots of other Riemann shapes. Those shapes are going to have different dimensions than the dimension that we've seen before, not just like 1D or 2D objects, but maybe thinking in a more general sense about how do we add up objects to get to a new object. So this is sort of our kind of our first look at that, which will still be in your comfort zone, but it will be coming up in fact, our very next video for section 6.2. We'll see that we can add up things other than just Riemann rectangles to find quantities of interest here. So I do think this section is relatively easy. I don't mean that it's easy, but I do mean that this shouldn't be too crazy here. I think algebra is going to be really important. Thinking in terms of Riemann objects is going to be really important. The integration itself won't be too crazy. All right, so and our section 6.2 video will be slightly longer. So I'm gonna do a couple of good representative examples today, but not get too crazy with this here. So what we're kind of going to think about today is we're going to visualize what we're doing heavily. We want to have a good graphical sense of what we're doing, and I like to think of some graphical subtractions that we do when we perform integration. There's sort of two different classes of subtraction where we're going to perform some horizontal subtraction between quantities with integration. That's stuff that you guys have already done. Today, our actual topic of interest for area between curves, we're going to do some vertical subtraction between some quantities. That'll actually be the new idea. So what I kind of want to start with today is just to say one version of subtraction that you've already seen with integrals is what I'm referring to as horizontal subtraction right here. And this is really just what we mean when we have bounds of integration. So I kind of want to throw an example at you guys as to when I teach this in other classes besides just this class here, and also kind of present an issue for us that we're going to want to think about over the course of this semester here. So one of the difficulties that I have, so I really like teaching statistics as well as just teaching calculus, but it's very different. And one of my big dilemmas when I teach statistics is that it turns out that like every quantity of interest in statistics is, it's actually something that came from calculus. But mostly every student that takes their introductory statistics class has taken no calculus. And so I can't describe things to them in calculus terms, despite the fact that that's really where it's coming from. So one of the most important distributions, probability distributions for like all of science, and it's the one that we use the most heavily in an introductory statistics class because it is the one that kind of occurs most commonly in nature, is the normal distribution, right? It's also known as the Gaussian distribution, or I think people use the sort of layman's representation of just the bell-shaped curve. That's a little more generic right there, but whatever. I think we've all kind of seen this, right? So the equation for this bell-shaped curve looks like this right here, which kind of sucks. What this is saying is that if a probability distribution is normally distributed, and I say normal like sort of with the capital L there, the formal, the normal distribution, if it has an average of mu and a standard deviation of sigma, then this equation right there will produce the bell-shaped curve that is centered at mu and experiences one standard deviation's distance away of sigma. The unfortunate thing is that this equation is super difficult to deal with as a standalone thing. And even worse than that, what we're really interested in when we're computing probability is not just what does the curve look like, or as this function would tell us, what is the height of the curve at any given point. It turns out that that's not really an interesting quantity for us in statistics. What we're really interested in is the area that's underneath the curve to compute the probability associated with a certain event, right? So what we're actually typically interested in here, where's the pen? Pen? Hello? That's on. Where isn't my pen again? I know you can tell it needs to be plugged in, computer. There we are. Okay. I was worried I was going to have to throw a tantrum there. All right, I got my pen back. So here we are. So we're looking at this normal curve out here, right? Uh-oh, why is my pen doing weird stuff? Okay. I don't really trust you, pen, but okay. All right. This is not like my normal pen. Why is it being different now? Okay, stick with me here, pen. So I got my normal curve here, right? And so my typical example that I like to kind of generally use in statistics is talking about a variable x being normally distributed. So we use the tilde to, and again, I'm kind of talking about stat stuff right here, but I think this is within reason that you guys can understand this here. So this is typically noted that a variable x is distributed according to the normal distribution with an average of mu and a standard deviation of sigma. One of the ones that I typically like to talk about is that adult male height is normally distributed with an average of about 5'10" and with a standard deviation of about 2.5 inches. I think those numbers are approximately correct right there. So what we could do is we could draw our associated normal curve here that has like a centered at 5'10", and we could ask ourselves questions like, what is the probability that a randomly selected person is shorter than 5'8", right, or a randomly selected male? And so to compute that value, we might locate where 5'8" is on the axis right here and identify that this area to the left of 5'8", that represents the probability of a person being shorter than 5'8" right there. So that's the probability that a person's height is going to be less than 5'8", however much area is underneath that thing. What you guys know, because you're calculus students, is that area underneath the curve is associated with an integral. But the big problem here is that I can't actually basically do this, right? So what I'm going to do is I'm going to show you why I can't really do this. So kind of one thing to notice here is let's strip away all the unnecessary stuff with this equation. Sigma, constant. Square root of 2 pi, constant. E to the power of, that looks like a function I'm used to seeing, negative 1/2 multiple, that's a constant. Mu, constant. Sigma, constant. It looks like the x term, though, is getting squared. That will like affect our integration meaningfully as opposed to all these additions, subtractions, multiplications that don't affect how we do our integration. So it seems to me like the essential function that's happening in here is an e to the negative x squared. That's the kind of baseline function that I'm seeing here. All right, so we are interested in doing something like negative infinity up to this 5'8" of that f of x function right there. And I will say that this is pretty similar to needing to be able to do this integral, right? If you could compute this integral, then certainly you could just do some like u subs and stuff to handle the constants and stuff like that that otherwise exist in here. So the bottom line is, if I were going to find the area underneath the normal curve, which is like one of the most desired quantities in all of statistics, what's the probability of an event occurring that is distributed normally, I need to be able to integrate this guy. And what you should be thinking to yourself is, okay, I don't know an antiderivative for e to the negative x squared. What I'm thinking to myself is what I want to do is I feel like I want to do a u sub where I'm going to pick like x squared to be u. But if I do this, notice that what's du need to be? It needs to be 2x dx. And that is missing, right? We don't have an additional multiple of x. If there's an x sitting right in front of this e right here, then you can for sure do the u sub and make this guy happen, but we don't have that. So the problem is that this most desirable function to integrate is literally not integrable. And that's a pretty huge bummer right there. So it turns out that this is kind of one of the reasons why we just have to get all of these computations out of our calculator. If you've taken statistics, then you know that tons of times you're just going to Excel, going to your TI calculator and saying, give me this normal probability, and it's just spitting out some decimals at you. Well, what it's really doing is it's really making an approximation to this integral right here, because we can't actually find a closed form solution for this integral. Like the u sub doesn't quite work out, right? So this is a bummer. Non-integrable, the normal distribution, probability distribution function right there. But that's okay, all right? I'm gonna show you at the very, very end of this video a slick little roundabout way that this can be, in a sense, avoided. And we will also talk at the very, 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 very end of this class, like literally the last week of this class, we will finally arrive at an alternate technique for attempting to compute some values that are like this. But again, directly, this isn't integrable. It's kind of a bummer. So the kind of thing I'm trying to say here is, even when I'm in my stats class, I couldn't present to them the calculus idea that the quantity of interest really is an integral. But even if I could, we can't do the integral anyway. So we're still a little bit stuck, right? So what I don't do in my stats class is I don't tell them all this calculus stuff. I just generically define what I refer to as a cumulative probability function. And this is exactly just an integral. I just say to them, listen, imagine in your heads that this CP of X function is going to give us the cumulative area up until some location X. For example, 5'8". That might be my X value right there. And again, since they're stat students, they don't know that what I'm referring to is an integral, but this helps me compute some values of interest for them, helps me write a way to express some things. And here we go, come to bring this back around to the horizontal subtraction idea that I had before. So I do this, for example, to show them that if we wanted to know the probability that a randomly selected person is between 70 and 72 inches tall, that we can express this as a subtraction of two cumulative probabilities, a subtraction of what you know to be two integrals, right? So I can think, and so 72 inches tall, right, so I'm going to draw a couple normal curves here. All right. So all these are supposed to be the same, right? They're all centered at the exact same location right here. And I'm thinking to myself, this should be 6'2" there, right? So that's actually a little bit taller than average. So 6'2" to the left of 72 is going to be all this area that's over here. Right, there's my 72. I can find 70, which should be a little bit closer to this thing because that's exactly 6 feet tall. So there's maybe my 70 right there. And what you can see is you know how to think about this horizontal subtraction anyway already, because this is really just our relationship between our bounds of integration, right? This is really just like saying, instead of doing an integral from negative infinity up to 72, subtracting off the integral from negative infinity up to 70, we instead just do things like the integral from 70 to 72 right there. Oh, am I doing my math wrong right there? You're right. Okay, yeah, that's 6 feet tall. That's actually 5'10". Thank you for that. I feel like I can fix this. Wait a minute. What? Did I not just select? Oh, okay. There we go. There's actually my. Yeah, I can't do my division by 12 this morning, it seems. So there's our 70. We're actually centered at 70 right there. There's still our 72 because that's 6 feet tall. Therefore, 70 is the 5'10" that we said that we're centered at. Okay. And so now what we're going to see is that all we're going to be left with is just this strip right here between 70 and 72, right? So I can present this idea pretty easily to my statistics students because I'm not suggesting anything about an integral. I'm showing them the graphical subtraction that's happening. And that's the thing that I'm trying to kind of like emphasize to you guys, that there's a picture here. I could take an amount of area, I can subtract off an amount of area, and all we're left with is the remaining area that hasn't been subtracted off. You guys understand this to be integrals from negative infinity up to an amount minus an integral from negative infinity up to an amount is the same as an integral from just the a to b, the two amounts that we ended at right there, all right? So this is kind of, I'm trying to kind of broadly express this idea of horizontal subtraction, is graphical subtraction, but it's happening from left to right. It's just handled by bounds of integration. It's just an X deal, right? Our real goal for today is to talk about the other form of subtraction here, or what I'm referring to as vertical subtraction, although I will point out to you guys after this, these are probably kind of bad names for this, but I'm trying to just kind of contrast two things that are kind of related here. This is going to help us find some area between curves, all right? So what I want to do is I want to do kind of this exact same idea right here, but we're going to do it from a different direction right here. So suppose we'd like to know the area between y equals x squared and y equals square root of x on the interval 0 to 1. All right. What I want to do is I'm going to draw the sequence of graphs that represent this area computation the same way that I drew it up above, so that we can see that there's still this idea of a graphical subtraction that's happening right here. And then I'll state the integral that represents that area. Right. So I'm thinking to myself, I'm going to draw like a kind of a sequence of graphs here. All right. So I'm thinking, I know that we're only interested in 0 to 1, so this will all be first quadrant stuff. I know that the square root of x graph looks like this guy. That's our square root of x. And I know that x squared looks like this guy. Right? And I know that those guys are going to meet right there at 1. Right? At 1, 1, in fact. So what I can see that I want to do, if I'm interested in this area in the middle here, then it looks like what I want to be doing is it looks like I should be doing the upper function here, and from 0 to 1, square root of x is actually larger than x squared. Remember that square rooting actually makes small numbers bigger. Bigger numbers between 0 and 1 get larger when you take their square root. So it's actually larger than squaring. And in fact, squaring makes numbers smaller when they're between 0 and 1. Sort of the inverse of the way that we typically think of the relationship there. So what I'm kind of seeing for myself here is I could be taking this square root of x area out to 1. Find this area. Oh, I wish my pen worked today. Unfortunate. I can subtract off now the square root of x area. And exactly what I'm going to be left with is exactly the area that is in between those two curves. That's right there. Right. So there's still a subtraction that's going on, and the nice thing is that this is still going to just represent the difference of two integrals, exactly kind of as we verbally expressed these guys up here as well. Right. So when I'm trying to find the area between two curves, I can find all of the area underneath the upper function, the one that's on top, and then subtract off the area underneath the lower function to chop off the parts I don't want to just leave me with the stuff that's going to be in between. And that's kind of our broad concept as to how we're going to approach this. There's going to be some differences in how we actually execute, but I think this picture does a good job of kind of generically representing our conceptual subtraction that we're doing associated with these guys here. Right? So this one, oh, and I do want to, I guess, state what we're actually looking at here. So it looks like this should be the integral from 0 to 1 of square root of x dx minus the integral from 0 to 1 x squared dx. And therefore, since these integrals are both integrals in dx, they are both over the exact same bounds of integration, I can perform this subtraction within the integrand. So it looks like we're going to be getting the integral from 0 to 1 of square root of x minus x squared dx, where the x squared is the upper function, or sorry, the square root of x is the upper function and x squared is the lower function right there. Right? We just took the difference of the two and we're going to find their area here. So that integral, you guys can do that integral. That one's a little bit less exciting. Let's just do a more exciting example for the sake of actually doing an integration right here, right? That integral is not super exciting to do. So let's set ourselves up with a slightly more interesting problem here. I want to determine the area in the first quadrant bounded by the same two curves, but let's extend how far out we're going to go here. I want to bound this thing by the line x equals 4 rather than just say it's the region that's bounded between the two. I'm going to go all the way out to x equals 4 instead of just stopping at x equals 1 as happened above right there. So in this case now, I'll do my best at this picture here. This will be a tough one to draw well. But we should have our x squared function out here. Yeah, that was pretty good. And we should, that's actually not going to, well, I'll leave it like that. And we'll have our square root function right here as well. So I know this is my square root of x. This is my x squared. And what I know is that that point right there, so I'm going to need to drag this out, is at 1. Right? That's 1, 1 right there. But what I know, and this graph is not going to be excellent for our... This is a hard graph for me to draw right there. This is a terrible axis, but I want to get my visual sense of what's happening right here, right? So I'm ending this thing at x equals 4, right? So what we're interested in is really this area that goes this entire way. So the thing that you need to notice is happening right here is that what we defined our integral here as the upper function minus the lower function over some bounds. And the very important thing that's happening here is that we can see which function is on top changes at x equals 1. So what that means to me is that I'm really going to have to build more than one integral to help me figure this out. I'm going to have one integral from the bounds of 0 to 1 where the square root function is on top. The second integral is going to have the x squared function on top from 1 out to 4 out there. So what I want to do is I want to get back in tune with my Riemann sticks right here. All right, there are two Riemann sticks of interest to us in this diagram here. And I want to identify both of these. I'm going to call this R1 and I'm going to call this guy R2 right here just so we can think about what their heights actually are. When we're talking about Riemann stick 1, the sticks that we want to be adding up to get our area, you should be thinking of your Riemann sum. We just have floating rectangles in space, not ones that are all just sitting on the x-axis now. What I can see here is that our width is still that same delta x. I know that my lower bound right here, the bottom of R1 is the x squared function, and the top of R1 is the square root of x function. On the other hand, for R2, this stick is also going to be delta x wide or dx wide, but it has flipped what the measurements are. Now the top part of this stick is actually the x squared function, and the bottom part of this stick is actually the square root of x function. So I can do these two different subtractions with these two integrals to go ahead and evaluate the overall amount of area associated with this, right? So I might call this region here like A, and this guy right here should be region B, right? So if we can add up the area associated with each of those intervals right there, then we should be good to go to compute this integral right here, to find this associated area. So I'm just going to say here, maybe I'll express this as our area is region A stuff plus region B stuff. And I'm gonna go kind of like long form on this guy right here. But I just want to kind of make sure that we see everything we want to be able to see from this guy. So it looks like this should be our integral from 0 to 1. And this should be our upper function here of the square root of x minus x squared dx. We're adding on to that because we want to additionally get a whole nother region's worth of area out here. This guy is going to go from 1 to 4, but in this case, we have that the x squared function is now on top and the square root function is the one that's on the bottom for the subtraction that we're performing there. So here, because we flipped which function was on top partway through the desired interval, we needed to make sure that we kept track of that for our area between. So it's really like two different shapes that we're getting here, which is why we got two different integrals. Now that we have this set up, I think that we can cruise along with our antiderivative here. So what am I seeing here? This is really x to the 1/2. So I'm going to go ahead and add 1 to the power. So this is going to give me an x to the 3/2. But I only want one copy of x to the 3/2, I only want one copy of square root of x if I were to take this derivative. I know that if I were to take this derivative, a 3/2 would pop down. So I'm going to introduce a 2/3 to counteract the 3/2 from the derivative to get back up there. Similarly, we should be getting a 1/3 x cubed because this has the derivative of x squared. Notice that this guy here, we are evaluating from x equals 0 to x equals 1. And we're going to get a similar quantity over here. We're just going to get different bounds, right? Oops, I'm doing it backwards right there. I'm forgetting that we're switched right here. So I'm going to get the opposite terms, right? 1/3 x cubed, that's associated with x squared, minus the 2/3 x to the 3/2. And this guy we will evaluate from x equals 1 to x equals 4. So let's go ahead and do the evaluating now. This is the easy part. And in fact, this is the extra easy part right here. Plugging in 0 makes everything go to 0. Plugging in 1 means just keep your coefficients. So this is just going to be 2/3 minus 1/3. minus 0. That's our first chunk. Our second chunk over here, I'm actually going to have to do a little bit of math, unfortunately, here. I got 4 cubed, which is 64. So that's going to be a 64 thirds minus 4 to the 3 halves. I'm thinking of 4 to the 3 halves as 4 to the 1 half cubed. 4 to the 1 half is the square root of 4, which is 2. 2 cubed is going to be 8. So it looks like I'm going to get 8 when I plug in 4 into x to the 3 halves. 8 times 2 thirds is going to give me 16 thirds. Let's see here. Minus, now I'm plugging in 1 into these guys here, so I'll get a 1/3 minus 2 thirds. All right, let's just add some fractions. We're done here. Oh my gosh, they're all in terms of thirds. That's awesome. So I'm going to get a 1/3 plus 64 minus 16. That's 54. That's 48 thirds. And then we're subtracting off. Notice we're subtracting a negative 1/3. So that's really adding 1/3. So I'm seeing here 50 thirds. 50 thirds seems to be the total area between these two curves from 0 all the way out to 4. One lobe from 0 to 1, and then another region here with the vertical bar on it from 1 to 4. And again, we had to keep track of which one was on top and which one was on bottom. By the way, I did skip an important step right here that you guys are probably going to have to actually do for some later ones. This intersection location of 1, 1, that was sort of trivially easy for me to identify with square root of x and with x squared. But notice that it's likely going to be the case that you're going to actually have to solve for where these locations are at and some other problems that you're doing. So notice all we really have to do is set these two equations equal to each other to find their intersection. So notice that we can do things like square root of x equals x squared. I'm going to square both sides, and I'm going to get x equals x to the 4th. X to the 4th minus x equals 0. That gives me x times x cubed minus 1 equals 0. And that tells me that x equals 0 and x equals 1 are the two places where they will intersect. And we do see exactly that. 0 and 1 are the two intersection locations. So just kind of realize, in this one, I don't think it was necessary for me to show that work right there, but I think you will encounter others where one of your key steps is going to be to say, well, we need to solve for where that breakdown actually ends up happening at. So just realize that I kind of glossed over that step because it was easy here, but you'll probably have to do that in the future there. So this was good. We did our graphical subtraction, a vertical subtraction right there. Yeah, so Austin's asking, can we do this one in terms of y to where we are solving these? So instead of writing these like y equals x squared and y equals square root of x, doing these with horizontal bars. And what I'll say to you is, well, let's just do that one in the next example. The answer is definitely yes. And I've got us set up to do exactly that in our very next example right here. So I'm going to say here, let's do this one two ways. Let's do it with the vertical sticks and let's do it with the horizontal sticks. And you're thinking the right thing here. The reason that you're asking that question is, I mean, it's great that you're asking that question because the whole point is we want to be comfortable changing what our Riemann object is that we're using. Here, our Riemann object I chose was a vertical stick that was infinitely narrow horizontally, so a dx width. But it should be the case that we could do a horizontal Riemann stick that has dy as its height right there and has a measurable width instead. Should have been just as reasonable for us to do so right there. So that is something we should do. We'll do that in our next example. So just my conclusion to this one is just say, when I call that vertical subtraction, that's a bad name because that name would be good only if we worked with y equals equations with integrals, but that's not always going to be the case. If we get x equals equations, then it might be the case that we want to do horizontal bars, and we can do that as well. So let's go ahead and take a look at that example here. So this is in section 6.1. This is number 4 in the book right here. And number 4 just says, find the area. I'm the one that's saying I want us to be able to express this both ways here. So let's find the area of the region bounded by these two quadratics. Now these two equations are certainly quadratic, but they're quadratic in y, not quadratic in x. So what you should be picturing is that normally when we have y equals equations that are quadratic, it gives us parabolas that open up and down. Therefore, these ones should open left and right. I'm thinking to myself, this is probably a good time for us to go ask Desmos what the heck this thing actually looks like here. So let's pop over to Desmos here. Cool, still got my audio. And let's go ahead and throw in these two equations into Desmos here. So I've got x equals y squared minus 4y x equals y squared minus 4y. And our other equation of interest is x equals 2y minus y squared. X equals 2y minus y squared. So I am seeing two parabolas opening left and right. Notice that this is a positive y squared and this is a negative y squared. So it makes sense that one is opening left and one is opening right. And so I can see clearly what the region of interest is now. And I want to find this stuff that's sitting in here in the intersection of the two. I can see that there are going to be some points of intersection that are going to be of interest to us here that we're going to kind of need to pay attention to. But I think for right now, all I kind of really want to do is just grab this thing and bring it into our document so I can write on it here. So I'm just going to grab this picture here. Snip, and let's bring it over here because I want to draw my Riemann stick pictures. So let's come back now to Word. I've got my picture here. And let's get our pictures going on for our Riemann sticks. One of them, let's get a second one here so I can do it again, and then a third one just in case I mess my picture up here since I'm going to draw on top of these guys. Get out of here, picture. All right, so let's kind of draw these and get an idea for where these locations are at, right? So again, we should be able to set these equations equal to each other and solve to determine where those locations of what? That was weird. Okay, I'm definitely writing here, so why are you putting that stick right there? Man, come on, pen. It just... Okay, so back to solving here. Setting these equal to each other, y squared minus 4y equals 2y minus y squared. I'm going to add the y squared over, subtract a y squared over. I'm seeing here 2y squared equals 6y. I guess I want to move them all together and factor, right? But we're going to get a y squared minus 3y equals 0. It certainly seems to be the case that at y equals 3 and at y equals 0 is where we're seeing these intersections happen right here. Plugging back in 3 into either of these equations, that's going to help us see that our point of intersection of interest there is that 3, 3 location, right? So we got to be careful here when we go ahead and we draw our Riemann sticks for this guy. We want to think about what this is actually going to look like when we make our vertical and our horizontal Riemann sticks here. When I draw my vertical Riemann sticks, notice what kind of my issue is going to be. When we're trying to find this area between, I want to keep on measuring what the upper function is and what the lower function is, so that I'm always taking the top function and subtracting off the bottom function. But notice that as we move left to right for our vertical Riemann sticks, that keeps changing. Right? The first Riemann stick that I feel like I want to draw right here has as its top part, the top of the red curve, and has as its bottom, the bottom of the red curve. Well, that's kind of going to be a little bit weird right there. It looks like we're going to have to do some solving to figure out how we distinguish between the top and the bottom right there. Then, as soon as we pass through this location, and by the way, it looks like this is going to y equals -4 here. So it looks like from -4 to -3, this is a good Riemann stick. But once we hit -3 right here, oh wait, by the way, why didn't I get a... Why did I get a positive y for... Oh, sorry, the y is +3. The x is what's -3. At x equals -3, then it's going to change. Now the blue function is on top and the red function is on bottom. So that's going to be our next chunk's vertical Riemann stick. And then once we pass through 0 again, it's going to change again because red is on bottom until we hit 0. And now blue comes to be on bottom right there. So it looks like in this case here, we've got really 3 different regions of interest. So this says to me, the vertical Riemann stick route doesn't look to be the cleaner of the 2 routes right here. I've got 3 different chunks that I've got to be able to add up there if we use vertical Riemann sticks. On the other hand, you should notice that if we're choosing horizontal Riemann sticks, what I'm seeing here is that means that we want to be considering what's the left function and what's the right function. Well, that never changes over the entire course of this object that's in the middle, right? There is just one representative Riemann stick that is associated with this entire region, and it just looks like that guy. It's just the red function on the left and the blue function on the right, right? So this is good because this says to me I only have one region of interest to integrate over. If we're doing horizontal Riemann sticks, we want to add up one for each of the associated heights. So this would be our 0 to 3 right here. And I feel like I want to name some of these things right here. This is x equals 0 to x equals 3. Over here we have y equals -4, -3, 0, and 1. And I'm going to go ahead and call these regions here A, B, C, and D, just so that we all have like a verbal reference for the things that we're looking at right here. So I kind of want to identify some of these things that we're looking at here, right? So like I feel like I need to like name a few more things so I don't get lost here. So one of the things I want to do is I feel like I need to identify which of these functions is which, because in a minute I need to identify like which one's upper and lower. One of the things that I'm seeing is that this top function right here has the positive y squared, so it should be opening up along the positive x-axis. So this to me looks like the red function right here. So this is our I'm going to call this our red function, and this is our blue function. This is our red function, and this is our blue function here, right? And I know that because positive y squared means open along the positive x-axis, just like positive x squared says open along the positive y-axis with an upward parabola. And very similar. Oh, wait, what was that? What was that stupid label right there? Who's letting me label this thing? That's not the x blue. This is our x blue right here. And this is our x red, and this is our x blue. Right? So it should be the case that we should be able to do this two different ways, right? The area associated with regions A, B, and C should be equal to the area, which should just be associated with just the way that we've described region D on the other hand side over there, right? We should be able to come at this two different ways. Right? So I am thinking to myself, and I haven't done the algebra that I need to do yet here, by the way, which is kind of going to be one of our little sticking points right here. Since I am adding up vertical Riemann sticks here, I know that I want one Riemann stick for every x value. So that says to me, I know that I want these integrals here to be defined based on their... Well, I feel like I'm labeling everything backwards here. Why am I labeling so many things backwards here? Why am I labeling x's as y's and y's as x's and reds as blues and... Oh my goodness. My pen bothering me has got me all flustered here. Those are obviously x values on the x-axis and obviously y values on the y-axis right here. So it looks like I can make my generic statements here as... I'm going to just kind of get some general stuff written down here. -4 to -3, there's going to be something I want. There's going to be some y stuff that we want here, and it's going to be a dx integral. We're going to add that to an integral from -3 to 0, again, of some y stuff. I don't know what it is yet. We're going to talk about it in a minute, dx. And we're going to add on to that an integral from 0 to 1 of some y stuff, dx. All right, we got to figure out all our y stuffs, but this is the general structure of our vertical Riemann stick example. And it should be the case that this is equal to, looking at an integral here, my y value is going from 0 to 3. That's a dy integral, and therefore this should be some x stuff inside of our integral. All right, x times y, that's your width times height. That's your area of a given rectangle that we've got right there. So it seems like we can go ahead and figure out what our upper minus our lower is for each of these chunks. And I do want to say, it very much looks like our horizontal Riemann sticks here is the cleaner way to do this problem. So let's go ahead and do that one first and then do the harder version, the vertical sticks, second here. So what I'm thinking for my x stuff here is I'm always wanting to subtract the upper minus the lower. But when we're looking at horizontal Riemann sticks, upper is going to mean further to the right and lower is going to mean further to the left. It's the one that's, I don't know, more positive over here. So it seems to me like what this guy should be right here is our blue curve, right? Again, for, or x sub b, if you can't see the red and the blue right there, minus our x sub r right there. That is my description of the y values. It's the, excuse me, that is my description of the x values right here. It's x sub b minus x sub r. The good news for us is that we have equations for these things in terms of y so that we can actually perform this integration. So let's go ahead and do this one here since, again, this is the slightly easier one right here. So my x sub b, that is 2y minus y squared. That is my rightmost function, 2y minus y squared. Minus our left function, which is the red function, the end of its length measurement right there. That'll be red. That's y squared minus 4y. So let's go ahead and do the integration here. And always doing as much algebra as I can first. It looks like that's a negative 2y squared, and then 2y plus 4y is going to give me plus 6y total. Doing the integration, I'm going to get a negative, a 1/3 is going to pop down. Right? Y squared, integral of y squared is going to give me 1/3 y cubed. I'm keeping the negative 2 along for the ride. 6y should go to 3y squared. And we're doing this guy from y equals 0 to y equals 3. And so I'm going to go ahead and plug in those values here. 0 is the super easy one, just nothing's happening at 0. Plugging in 3, I'm going to get negative 2/3 times 3 cubed plus 3 times 3 squared. So 3, this is going to be our 27 right here. All right, 3 times 3 times 3 is 27. I'm seeing here, I think I'm going to cancel a 3 and make that squared right there. So maybe this looks to me to be 3 squared is 9 times 2 is 18, and that's a negative. So it looks like, man, and this always kind of blows me away whenever we're looking at kind of funny shaped things like area between parabolas, and then you just get an integer answer. It's always kind of crazy to me right there. So it looks like I'm finding that the area between these two parabolas is just 9. That's what I'm expecting to get when I go ahead and do the, you should notice here I left 3/4 of my page width for the other side that's over here. So if we're going to do this other one here, remember that kind of one of our issues is that it looks like we have upper and lower bounds that are each representative of one parabola, which is kind of weird. But what's going to turn out here is that when we solve these quadratic equations for their opposite variable, right, we need to have y equations to plug in here, and these are not currently solved for y. It seems like we're going to have some plus or minus square roots that are going to represent top half and bottom half of these shapes that we're looking at here. So let's go ahead and take our two equations and let's go ahead and solve them for their appropriate variable. I need y equations in here, so I need to go ahead and solve this guy because I want an expression in terms of x so that I can integrate it to dx right here. All right, so one of my equations here is x equals, this is our, what do we got? Y squared minus 4y. So my job is to solve this thing for y. So what I think I'm going to do here is complete the square and solve. All right, so I'm going to go ahead and do x equals y squared minus 4y. If I am completing the square, I divide negative 4 by 2 to get negative 2. I square it to get positive 4. So I know that what I want here is a plus 4. I need to go ahead and subtract 4 to go ahead and account for the fact that I added 4. These three terms are going to go ahead and be a completable square. And now I can go ahead and solve for y and get an expression in terms of x. So I'm thinking here we're going to end up with x plus 4. We're going to get a square root. We're going to get a plus or minus. And we're going to get a plus 2. And that should be my y for that first guy right there. 2 plus or minus square root of x plus 4. For the other equation here, we are looking at x equals 2y minus y squared. And by the way, so I just want to show you, maybe I'll just do this a different way. I'm assuming that a handful of people right now are like, oh crap, I don't remember how to complete the square. If that's you, then you should recognize that there is other ways that we can solve since this is quadratic. A different thing I could do is I could move everything so that this is equal to 0. So I might rewrite this as y squared minus 2y plus x equals 0. In this case, I have a quadratic with a equals 1, b equals negative 2, c equals x right there. And I can just go to the quadratic formula here. Y equals negative b plus or minus square root of b squared minus 4 times a, which is just 1, so I'll skip it, times c, which is x, all over 2a, which is just 2. And notice we could factor out the 4 underneath the square root as a 2 outside the square root. Now I've got a 2 here, a 2 is a coefficient, and a 2 in the denominator. So it looks like this guy will simplify down to 1 plus or minus square root of 1 minus x. Right? So just two different techniques that we could use to solve that quadratic for the opposite variable right there. Either complete the square and solve, or get everything on one side homogenized by making it equal to 0 and then using the quadratic formula right there. So now that I've got my two y equals equations, you can see that plus or minus. That's giving us, for those pluses and minuses now, the plus is always going to be the top part of our sideways parabola, and that minus is going to be that bottom part that lives down there. So now we have sort of like a sensible way to perform this subtraction that we are wanting to set up for ourselves here. Right? So now I gotta get now I gotta be even more specific with these integrals that we set up for ourselves here. So maybe what I should do here is I'm going to leave this here so that we can like reference it again. I don't know what to do about this. I don't know why my pen is different today than it's ever been before. When I draw on here, why does that shape move? Okay, so we have our three representative Riemann rectangles that magically are allowed to be drawn on my graph all of a sudden now. And we know that we're looking to add up the area of those three regions right there, the -4 to -3, -4 to -3. At -3, we switch which function's on top. Then we go from -3 to 0. It's the same functions are on top and bottom from -3 to 0. But at 0, we switch which function is on the bottom right there. So knowing that I'm describing this, this as our red and this as our blue right here, so even if you can't see my colors right there. And by the way, if I didn't say this in the last week's videos, if anybody does have any color issues, if for any reason you can't see these colors, if there's any colors that would work better, just let me know, and and I can definitely make any of these things be any of the colors that they need to be. I don't want to discount anybody if you have any version of color blindness or any other issue that makes seeing these things difficult right here. So so here's kind of what I'm seeing. Let's write out a couple more word integrals right now to kind of get me going. So from -4 to -3, what do I really want? Well, it looks like what I want is the red upper minus the red lower. Right? And this will be, and notice that we're doing this as a Riemann sticks that are vertical, so we're doing one for every x value. So this will be dx, right? -3 and -4 are x values of interest here. Adding to this, we're going to go from -3 to 0, and in this case, we've got blue upper as the top, minus red lower is the bottom. And for our third chunk here, we are looking at 0 to 1. And in this case, we have blue upper minus blue lower. So we already solved for all these things. We just got to sort of like assign them here now, right? So coming back over here, all right, this is one of our last references right here. Let's see, the red equation is the one with the positive y squared. So this was our red. And this one right here is our blue. So first integral, we want red upper minus red lower. Red upper is going to be the positive version of the square root. Red lower is going to be the negative version of the square root there. So I am seeing integral from -4. That's not going to let me do it, is it? Gosh. So red upper is going to be the positive version of the square root. So 2 plus square root of x minus 4. Minus red lower. Red lower is going to be the negative version of the square root. So 2 minus square root of x plus 4. Wait, is that an x plus 4 or x minus 4? That is an x plus 4. I just wrote it wrong. Actually, I don't think I wrote it wrong. This thing's just not picking up some of my pen inputs here, which is killing me. So there's our first integral setup. We got it right there. Let's write out the other ones, and then we can do the algebra and simplify these guys here. Next one up, blue upper. Blue upper is going to be 1 plus the square root of 1 minus x. Minus red lower. Red lower is 2 minus square root of x plus 4. For our final integral, from 0 to 1, blue upper minus blue lower. Blue upper is the plus, blue lower is the minus, so a 1 plus 1 minus root x. Minus 1 minus square root of 1 minus x. And notice that even though we're subtracting off terms that are like almost equal to each other, we're not actually getting any cancellation here because this is going to be a positive minus a negative. We're actually doubling up on the root terms that are in here. So it looks like here this is going to simplify down to 2 minus 2. Well, those did cancel, but we're going to get 2 copies of square root of x plus 4. Similarly over here, actually no, not similarly, this is the one where there is no real combination. 1 minus 2 is going to give me -1 plus square root of 1 minus x plus, again, square root of x plus 4. And for our third guy over here, again, 1 minus 1, those will cancel, but we will end up doubling up on that square root term. Right? So for each of these guys now, I do think that there's basically just like a little u-sub that we can do. I guess here's the thing that I'm noticing that's nice about this. This problem will tell us how to get our square root of x plus 4 integral. This one will tell us how to get our square root of 1 minus x integral. We can then maybe use these two like small easy ones to just help us get what we need to get for the middle right here. So I'm thinking to myself, I could do a quick little u-sub here, u equals x plus 4, and then du equals dx. And so that's going to allow me to write this as 2 integral -4 to -3. And those are x values right there. And that's going to be a u to the 1/2 du. So I'm going to end up with here, I add 1 to the power to get the 3/2. So I'm going to want to do the 2/3. And this will be evaluated from x equals -3 to x equals -4. And it looks like that's leaving me with 4/3 times. I'm going to plug in 4 into this guy right here, or excuse me, -4. Minus -3 to 3/2 right here. Gosh, I suppose I'm heavily anticipating some cancellation right here happening with some of these guys based on the fact that we can't compute -3 to the 3 halves. I know that we're looking for an answer of like 9 here. Um, oh no, I just committed the sin. I just committed the sin, and you guys didn't stop me right there. I just plugged in some x values in for you right there. Let me go fix that. Okay, so now it seems like we're getting 4/3. I'm going to plug in my upper bound is at -3, and that's just going to give me 1 to the 3 over 2 minus my lower bound, which is just going to give me 0 right there. Okay, so now I feel a lot better about that guy right there. I was like, what am I going to do with a 3 to the 3 halves power right there? That's not going to work out. So I see that I'm getting from this chunk right here just a 4/3. Similarly, I can go over here, handle this chunk in a very similar fashion. U equals x plus 4, u equals 1 minus x, du equals negative dx. So I'm going to move that negative over, and it looks like we're now looking at -2 integral of u to the 1/2 du. Notice that this negative sign has changed. That's from the negative that we picked up right there. Same thing, I'm going to get my -2 times, because that's going to be a 3 halves power, I'm going to do a 2/3 coefficient. Evaluated from x equals 0 to x equals 1. And it looks like this will be a -4/3. And now I'm going to not make the same mistake. 1 minus x to the 3 halves, evaluated from x equals 1 to x equals 0. Once again, I'm going to get some really nice things happening here. When I evaluate this guy at the upper bound, so this is going to be a -4/3 times, evaluating at the upper bound, when you plug in 1, we're just getting 0. And when we do our lower bound, we plug in 0. I'm just getting 1 to the 3 halves here. So it looks like there's my negative times the negative. It looks like we are also getting a contribution of 4/3 from this part. And so now I think I can see where we're headed with this guy right here. Notice that this is a nice representation of my antiderivative right here, with the exception of this had a multiple of 2 and this had a multiple of 2. So that means I'm really just going to get things like 2/3 x plus 4 to the 3 halves and 2/3, -2/3 1 minus x to the 3 halves right there. So I know my two antiderivatives. I think I can just reuse those now. So when I compute this integral right here, I think what I'm getting is a -x. That's coming from the -1 term. I am going to be getting the integral of 1 square root of 1 minus x. We just did this. It was -2/3 times 1 minus x to the 3 halves. And the square root of x plus 4, we already did this one. We got 2/3 x plus 4 to the 3 halves. Remember that 2 coefficient was part of that grouping, but not part of this grouping right there. So I'm going to get a plus 2/3 x plus 4 to the 3 halves. And we're evaluating this whole thing from -3 to 0 as x values right there. So I feel like I got to separate these guys out a little bit from each other. All right, so evaluating this guy at its upper bound of 0 is going to be giving me -0 minus 2/3 times just 1, right? I'm plugging in 0, so I just get a 0 for x, so I'm just getting a 1 to the 3 halves. And then I'm getting a plus 2/3 times the 4 to the 3 halves. We did this one a bit ago. 4 to the 3 halves is 8. So I think I'm going to get a plus 16/3 there. Minus, I'm now going to plug in -3 into this guy. So plugging in -3, it looks like I'm getting a positive 3. It looks like I'm getting 4 to the 3 halves, which is 8. So that's a -16/3. And it looks like I'm going to be plugging in -3 here to get 1. So that'll just be the plus 2/3 for that guy right there. So I think I just got to do some fraction math right here. It looks like I'm getting 14/3. Thinking of this as like 9/3. 9 minus 16 is -7. Plus 2 is -5/3. But I am adding, that's -5/3, but I'm subtracting -5/3. That's really +5/3. And therefore I'm getting 19/3, I believe. And now when we add all this guy together, 8 plus 19 is 27/3. Just like we got when we did it the easy way, right? So that was a really long roundabout way that we don't want to have to do, but in a sense, you should be able to do this, right? This is certainly an expectation that I have, that I'm going to say to you, like, state the integral that is equal to this area, or excuse me, state two integral expressions, one with horizontal Riemann sticks, one with vertical Riemann sticks, that both represent this area of interest right here. And a big lesson that you should be taking away from all this crap that we just did right here, I mean, look at all this. This was the amount of work required to do the answer the easy way. Just this little piece of work in the column right here, whereas this was all the work, and this, and all of this, all of this, all of this was all the work when we did our vertical Riemann sticks right here. So I hope that the kind of the lesson that you're taking away from this is, just because the first thing that you learned was vertical Riemann sticks doesn't objectively make vertical Riemann sticks better. In this case, the horizontal scenario was far superior because we didn't have to keep on transitioning what function was the upper and what one was the lower. When we did the horizontal sticks, it remained consistent the entire time, that it was just red function on the left, blue function on the right, and there wasn't any change over the interval of interest right there. So I think a big lesson to take away from this guy is almost more strategy than anything else. Don't pick the one that is going to be bad for you, right? So in terms of x with up and down facing parabolas, we can use either vertical or horizontal Riemann rectangles, totally. So your question is, like, if we were going to come back to this problem, we absolutely could have rewritten this problem in terms of the opposing variable and done everything again, and should be getting the same answer if we set everything up right there. So in all these ones, kind of the point is now with your question, the question is, can we? But I think the real question is, should we? So I really think that what you should be thinking now to yourself is, anytime you're in any one of these situations where you're just trying to find the area of some sort of blob out in space, it matters that you stop and say to yourself, is it going to be better for me to do vertical or horizontal rectangle sums right here? And I think that all you should really have to do is just draw these two pictures and then say to yourself, yep, I'm doing the horizontal way. Clearly going to be easier right there, especially because these equations were already given in terms of x equals and not y equals. So that's another kind of like, I was going to say a red flag. That's a green flag right there that says that horizontal sticks might be better if you're given equations in terms of x equals. It's a good chance that you might want to be doing the horizontal sticks instead. But again, strategy matters. Really the big point here is that there's several ways that you could approach the problem. And I think that what all of you guys just saw is one of them took literally 5 or 6 times as much work as the other route. Both of them are correct, but clearly one of them is better for you to be doing right here. But again, I expect you to be able to come up with these. So I don't think it's an unreasonable question for me to ask on a written homework something to say, state two different integral expressions, one in terms of dx, one in terms of dy, that represent blank area right there. Your answer, and especially if I just say, give me the integral expressions, your answers would just be, one of these two statements right here for your dy integral would be acceptable. And then this nice big gross statement right here would be your dx integral expression that would represent the exact same area right here. So I'll on next week I'll put out our first written homework, and I do intend for that to sort of be one of my questions that I'm asking there, is just state the integral expression that represents this, but think about it in both directions right there. So do be able to think about your Riemann sticks. Remember that the Riemann sticks are guiding us. If I don't draw these, it's really hard for me to think about what my measures are for like the length of each of the sticks and stuff like that. So think in terms of Riemann objects. As I've kind of said a couple times now, there are 4 different sections coming up for us in the future where we are going to be using Riemann objects. They're not going to be sticks anymore, to accumulate things of interest. And so in general, I think it's good for us to stop thinking of Riemann sticks as like a one-dimensional stick that we add up to get a 2-dimensional sheet, and instead think of a Riemann object as something that is an n-dimensional object. And if you add up an infinite number of n-dimensional objects that are all adjacent to each other, then you're going to get an n plus 1 dimensional object, right? Adding up a bunch of sticks gets you a 2-dimensional sheet. Adding up a bunch of 2-dimensional sheets is going to get you a volume. And that's exactly what it's sitting above my head right here. Tomorrow's discussion is volume. So rather than taking the integral of a height equation, because height times another length is going to be area, we'll take the integral of area equations, because area times an additional length is going to give you volume. And that's what we'll do tomorrow. Whew, so this one was good. This was a bit of a bear. This was a ton of algebraic work. I made like 7 mistakes along the way, but I got there, and I'm confident that I did it right because we got the same answer both ways. So, kind of last statements here. The book states there are formal areas between two curves as the absolute value of f of x minus g of x right here. All the absolute value is really doing for us in that more formal statement from the book right there is saying, make sure you subtract off the bottom from the top. Also remember, we subdivide into several regions whenever we switch which function is on top and bottom or left and right. And that's your kind of algebraic responsibility, is to be able to identify exactly where those locations are. I believe that my final takeaway, it was kind of funny, I kind of got ahead of myself. I knew that this was something I was supposed to be saying, and so I said it, and then here I scroll down, and here it's sitting, is right here. The theme of this section is trust your Riemann objects. You need to be drawing the object that is the thing of accumulation that's going inside of your integrals here. Never forget that an integral is just adding up lots of rectangles. It's just adding rectangles. That's all we're really doing. So defining the rectangle is key. If you're able to fully describe one rectangle, then you can build the associated integral. Maybe you can't actually do the integration, but that's why there's going to be tons of meaningful times this semester where all I'm going to say to you is state the integral that represents this quantity. Don't perform the integration. So many cases we can't actually do the integration ourselves, but at least being able to set these things up is for sure important. We're going to extend this many, many times. There's going to be 4 more sections this semester where we're going to use the same concept as we did today, just the general concept of integration, but what our Riemann object is going to continually change. So we're going to keep on saying, how do I find this? Well, think of a one-dimensional lower object that represents it and accumulate a bunch of them. And that's how we're going to identify things of interest, areas, volumes, arc lengths, amount of work that we perform, lots of these things out there. So an integral adds up an infinite number of adjacent n-dimensional objects to arrive at an n plus 1 dimensional object. If you want to know what I mean by adjacent right here, just go to grad school. They'll explain it to you in a few semesters. So very last thing I want to talk about here, just because I can't bring up that normal distribution from earlier and then abandon it, I do want to show you a super cool little roundabout trick that we can do here. This trick is technically something that requires a little bit of calculus 3 to actually pull off, but even if you haven't taken, obviously it hasn't, I'm thinking diffie Q stuff, but when you guys see this in Calc 3, I think you'll see this to be quite satisfying right there. So check this guy out. Candy Tree, what's going on? So if we're trying to perform this integration, the place where we get stuck is that we want to do the u sub, right? We want to do u equals x squared and then du be 2x dx, right? If that x was sitting right there, we'd be home free. This would be a piece of cake. I absolutely expect that the integral of x e to the negative x squared is an easy u sub for you to do. But without that x, it's literally impossible. So here's the sneaky trick that we can do. This is like a 2-dimensional graph, right? This is our normal curve sitting right there. What I think we should do instead is this. Extend this idea here to don't just think about a 2-dimensional drawing right here, but rotate this thing around so that we're now thinking of a 3-dimensional instead of a 2-dimensional object, right? So this is more like a 3-dimensional mound. Well, the cool thing is that I can make this guy happen right here. This is just the integral of e to the negative x squared plus y squared. I'm going to have to throw another integral on it, dx dy, all right? So I know that you guys haven't taken Calc 3 because you're in Calc 2, but all we're doing here is just layering integrals together, exactly the same as you can just layer derivatives together. This is just like you've taken a second derivative. This is like me taking a second integral. The only important difference here is that the variable with which we integrate changes. And with multiple derivatives, it's always with respect to that same one. So here's the cool thing you're going to learn in when you go take Calc 3. What I'm seeing here is I know x squared plus y squared is a quantity I've seen in math about a billion times, right? X squared plus y squared I think to myself as being r squared. That sounds to me like polar stuff. And in fact, you should be thinking what Riemann object would be good to get the volume of this 3D shape? Well, since it's a perfectly symmetric mound, it seems to me like there's a bunch of circular disks that are changing in radii over time, right? And that would be giving you that normal distribution shape right there. So what I think we could do is convert this guy into polar. There's going to be two important steps. One, this x squared plus y squared we could rewrite as r squared. The other incredibly important thing that you'll learn when you do your polar multiple integrals next semester when you take Calc 3, which by the way is way easier than it sounds. One of the very important translation steps that you'll learn is that dx, dy is not exactly the same thing as dr and d theta, right? And we convert from Cartesian to polar, we go from xy land to r theta land, but dx times dy is like an infinitesimally small rectangle, right? With x as its length and y as its width. You can't just multiply r and theta and say it's the same thing as multiplying x and y. One of the important concepts that I won't discuss here, but that will be like the critical part of that day's lesson in Calc 3, is that dx dy can be translated into polar as r dr d theta. Notice that by introducing that additional multiple of r, yes, Candy Tree, this is my Calc 2 class here, week 2 of the semester here, is that by introducing this, this is now equal to the double integral r e to the negative r squared dr d theta. And notice, now you can do the u sub you wanted to do. So one super sneaky roundabout way that we actually can find the area that's underneath the bell curve is we artificially extend it to have another variable involved. That's the y squared. We convert into polar because it introduces the additional r with the dr and the d theta. That r allows the u sub to happen. We now can perform the integration, so we do. And the only other step that you'll have to go learn now in an advanced probability class is we want to then just re-extract just the two-dimensional information only about x and not about y from that three-dimensional situation that we have created right there, right? But a super cool little like roundabout that we can do to say we needed more room to move around. We were kind of stuck with that u sub right there, so we added an extra dimension, which allowed us to do the maneuvering that we wanted to do, and then we can fall back into the one dimension that we wanted to be in that we originally started from right there. So there is some sneaky tricks that we can do to help make things more integrable. It seems weird that by introducing unnecessary variables, that helps make things more integrable. But integration's weird, so I guess I'm not too terribly surprised by that. So we will, as I said, one of our like literal last topics of this entire course, like 15 weeks from now, will be yeah, Candy, is that, sorry, I'll answer your question one second, is that we're going to talk about a different technique for getting, again, the value of this integral right here. That one's going to take a lot more work to build up. It'll be like, it's like section 12 of chapter 11. It's where we'll finally discuss that guy. But I will kind of keep on bringing this one up because I do like this probability topic. And yeah, so the question I'm seeing in class right here is this posted anywhere else? This is in my YouTube channel as well right here. And I might as well, I'm gonna throw that link in chat right now so that you can see that. And then you can find any of my stuff anywhere right there. So let's see here, show me more. Is this gonna take me to just my page right here? I think that it will. There we go. There we go. So there you go. There's my YouTube right there. It's got I've got trig stuff. I'm doing trig, calc 2, and differential equations this semester. So those are on there if you want access to those guys right there. Austin's also asking a good question. Austin, I was going to post a message about that in Canvas. I did. Basically, I was kind of going back and forth on assignment due dates before the semester started, and I ended up changing my mind about some things and then not reflecting that decision in some of the due dates. It was my intention for everything to be due this Saturday, but I accidentally left some of the due dates all the way through to next Saturday. But I think I'm just going to leave that now since I don't want anybody to feel conned if I go ahead and bump those due dates forward. It is my intention that our homework assignments are going to be due of the Saturday of that week rather than the Saturday of the following week. So it will be the case that the 6.1 and 6.2 homework will be due on the 30th as it currently states the 5.4 and 5.5 homework being due. That was just a mistake on my part and I'm just going to leave it there just because I don't want to catch anybody off guard with me technically tightening the deadline, since in some places I said 23rd, in some places I said 30th. The 30th was technically a mistake, but I am going to leave it that way. So if you want the extra time, you can. And I know I also assigned just a ton of stuff in week 1, so that's also why I'm fine with letting that go. But I appreciate you bringing that back up right there. Candy Tree, I am not teaching any computer science stuff, but I definitely do lots of programming things. I'm going to be doing a little bit of Python stuff for my differential equations class. That'll be happening here in like 35 minutes. And so I've been thinking about doing some programming things. Advent of Code is something that I do quite a lot of, spend some time on. So I have actually been thinking about streaming things other than just directly my course lectures. But yeah, I would need to be prompted as to what those things would be. So I'm into doing some more things out here. So, but yeah, I've got these. I'm doing 3 lectures a day on Thursdays and Fridays. So if that's something you're interested in hanging out for, I'm doing this publicly for a reason, so that anybody that wants access to this stuff can have it. So happy to have anybody here. So. However, as this is also a video that most people are watching not live right now, I am going to go ahead and wrap it up so that I don't just have 10 minutes of extra stuff that they don't care to see at the end. And I'll be doing my differential equations here in 35 minutes if that's something you're into. So for those of you that were all here live with me today, very cool. And nice, data science. I'm doing a bunch of data science stuff right now. Maybe we should be doing that together. Let's go with that. I've got some. I've been doing a bunch of pandas classes myself lately, doing some Python stuff. So that's in my ballpark as well, right there. So I'm going to go ahead and conclude the video now here for all of you non-synchronous watchers catching this on YouTube. And we're going to be hitting 6.2 in the next video, which will be volumes. We're going to be talking our Riemann objects in a more generic sense there, adding up areas to collect volume rather than adding up linear lengths to collect area instead. So I will see you guys for that next one right there. Have a good one, everybody.